Alrighty, section 10.4, inverse trig relations. The first thing we're going to figure out is what they are. And then we're going to figure out how to use inverse trig relations to find an angle measure. And then also we're going to take we're going to use trig functions in restricted domains. That's some fancy language. We'll figure that out in a minute. Starting off, we've evaluated trig functions for a given angle. Like we've done like the cosine of 30 degrees. Let me write that down. Cosine of 30 degrees is equal to the square root of 3 over 2. But what if, so that square root of 3 over 2 is just kind of like a ratio of side lengths of the right triangle. But what if we already know the ratio of the side lengths, but we don't know the angle measure? That's where inverse trig functions come into play. So the functions that we've talked about, sine, cosine, and tangent, they also have inverse functions. They're denoted with this like little -1 up here. We read this as sine inverse or inverse sine. I'll probably say like inverse sine of A equals theta. So if the sine of some angle, theta, equals A, then the inverse sine of A equals that angle theta. They kind of undo each other. We've seen this notation before with like inverse functions and whatnot. You've also seen it like if you've got the number 7. Then the inverse of that would be 7 to the -1st, or 1/7. They're inverses because they undo each other. These are 7 and 1/7 are multiplicative inverses because 7 times 1/7 equals 1. They kind of like undo each other. I just did air quotes on a video and that you guys aren't watching me on, but whatever. Just imagine me doing air quotes. So 7 times 1/7 gives us 1. They're multiplicative inverses because they get us back to 1. Sine and inverse sine are inverses of each other because they get back to the original angle. So we got cosine and inverse cosine. We got tangent and inverse tangent of A. Now, how we're going to use this, the inverses of the trig functions are not functions themselves because there are technically an infinite number of solutions of that or for theta for a particular value of A. So say, for example, you want to find the inverse cosine of 1/2. Based on what we've seen in the unit circle, yes, it's coming back, and yes, I'm going to give you a filled-in one for this week. Based on what we've seen in the unit circle, the angles that measure pi over 3 and 5 over 3 both have a cosine of 1/2. So remember, the cosine is the x value on your unit circle. So these are both solutions to this. You can't have multiple solutions in order for it to be a function. So this is not a function as is. In fact, these are just two of infinitely many, because we also have to talk about these things called coterminal angles. Remember, coterminal angles are angles that like start and stop at the same spot, but it doesn't matter how you get there. So say, for example, let me do a different color so it's a little easier to see. Let me do green. So say, for example, we're starting off at 0 radians. And if I were to do pi over 3, that's great. But if I could do another full circle and end up at the exact same spot, and so that would have the exact same x and y coordinates, so that is also going to be a solution. Same thing for the other angle. Any coterminal angle will also have the same solutions. Let's try an example out. I'm going to show you how we can use the unit circle. And again, I'm going to give you a unit circle now, and you're going to also have the tangents filled in on there as well. The first thing we're asked to find all possible values of the inverse cosine of the square root of 3 over 2. If you think back to a couple of minutes ago, you might remember one answer. So the first thing we're asked to do is find all the values between 0 and 2 pi radians, where cosine of theta equals square root of 3 over 2. In other words, like putting that just purely symbolically, where is the cosine of theta equal to the square root of 3 over 2? All right, so now we got to look at our unit circle. If you don't have it memorized, perfectly fine. Let's take a look at it. So we're looking for where the cosine. Remember, on our unit circle, the cosine is the x-coordinate. The sine is the y-coordinate. We'll talk about tangent in a little bit as well. Sorry, I accidentally had a line that I drew there as I was zooming in. So we're looking for where the inverse cosine of the square root of 3 over 2. We're looking for where cosine is equal to the square root of 3 over 2. We've got two options. One's right here, and one's right here. So we've got pi over 6 and 11 pi over 6. Let's jot that down. So two answers, again, pi over 6 and 11 pi over 6. Sorry, my computer's being slow. So we got theta equals, that was a weird looking theta. Let me try that again. Theta equals pi over 6 is one answer. And the other answer that we saw was 11 pi over 6. Now it says find all the angles that are coterminals with the angles measuring pi over 6 and 11 pi over 6. Thinking back to coterminal, we heavily focused on degrees. So like say for example pi over 6. Pi over 6 is 30 degrees. And I'll just write this down here. Now thinking back to what we did with degrees and coterminal angles, we just added 360 or subtracted 360. So we could say plus or minus 360, and since we do it over and over and over, we're going to say times n number of times. It could be plus 361 times 1, plus 360 times 2, plus 360 times a million, or minus all those. Now thinking back to what we know about the relationship between degrees and radians, if 30 degrees in pi over 6, again, from the unit circle, same thing, but 30 degrees in pi over 6, same thing. For 360, the radian equivalent is 2 pi. And similar to what we did with degrees, we're going to say it's 2 pi times n. So it could be 2 plus 2 pi minus 2 pi plus 2 times 2 pi, or 4 pi. So that's one of our answers describing all possible coterminal angles. Same deal with the 11 pi over 6. So we got theta equals 11 pi over 6 plus or minus 2 pi times n. So those are our two, well, technically infinitely many solutions. Now on the next example, we're going to try this out with tangent. We're asked to find all the possible tangents, or all the possible values of inverse tangent of 1. Going here, I'm such a nice guy. I gave you all the tangents. The tangents are the numbers on the outside here. Now, if you don't have the tangents given to you, remember tangent on the unit circle, a couple different ways you can think about it. It's the sine over the cosine, or in other words, y over x. So if you're ever stuck on that, you need to figure out what the tangent is, and you only have the x and y values, the cosines and sines. Take your y value divided by your x value. But I'm such a nice guy that I gave you all the tangents. You are welcome. So we got to go in a unit circle, find all the tangents that are equal to 1. There's one. There's another. So we got pi over 4 and 5 pi over 4. So we got inverse tangent of 1 equals, let's just call it theta. Our two solutions, we got pi over 4. Sorry, it's a sloppy looking pi. Let's try that again. Pi over 4 and 5 pi over 4. Sorry, I said 4 and I wrote 6. Similar to the last one, talking about coterminal angles. We're going to say plus or minus 2 pi times n. Now, technically in this case, it didn't tell us whether we're supposed to be using degrees or radians. So let's also do it in degrees. 45 degrees plus or minus 360 n. And the other one we got, let's see, off the top of my head, 225 degrees plus, oh my goodness, that was a weird mistake, 360 degrees times n. Plus or minus, same thing here, 360 degrees times n. So these are our two solutions. One version in radians, one version in degrees.